Alright guys, welcome to chapter 1. This one is mostly just review. In fact, actually, it's all review. So this one shouldn't be very painful at all. Atoms versus molecules. Give yourself a minute, see if you can remember what the difference is between an atom and a molecule. Yeah, well, first off, matter. You should already know that everything's made up of matter, and this really matters. Okay, so matter, all of it, is made of atoms. An atom is the smallest part of an element that's still that element. Clear as mud, right? Well, basically, atoms, atomos, used to, be thought of as indivisible. We now know we can divide the atom, but basically it is just the smallest piece of a particle that we can still call an element. So in the red ball you can see, well, gee, this is the oxygen atom and this is the hydrogen atom. Not too painful, we picture them as little balls. Now again, matter is made up of atoms, but a molecule, unlike an atom, is two or more atoms joined and acting as a single unit. So here we have a bond between the hydrogen and the oxygen atoms to give us a water molecule. And you should know already that if we were to write the oxygen molecule, well, it's one of those 7 diatomics. Do you remember all 7? Yeah, well, let me jot them down for you because you really need to know that when you see the word oxygen molecule, it's O2. So we write it as O2. And when we write the hydrogen molecule, there's 2 atoms fused together acting as a single unit, and it's written as H2. And you'll often see these instead of the words oxygen molecule, you'll see the word elemental oxygen. And these two things mean exactly the same thing. So back to the 7 diatomics. Did you write them down? Do you remember? All right, well, we have H2, O2. Got those. Those are on the board. Yeah, easy enough. N2, F2, Cl2, Br2, and I2. Seeing as how this is chemistry, we're going to focus a lot on chemical reactions, and it's how one substance changes to another. And all you got to do is reorganize the atoms. So here we have 2 water molecules. We run an electric current through it. We can separate it. We end up with 1 oxygen molecule and 2 hydrogen molecules. This is a chemical reaction because the little balls are rearranged, or in this case, reorganized. Now, if you remember, a measurement always has 2 parts. It has both a number and a unit. And you guys know how I am about both numbers and in terms of like the correct number of sig figs or units. Make sure you have a unit on all of your answers. So, for example, 20 grams or joules seconds. This is, by the way, a single unit. So let's see how your memory works. Do you remember the unit we use for mass? Yep, that would be grams. I wonder if this is actually on the slideshow. Nope. Do you remember the unit we use for length? Length. The unit for length. Well, if you said meter, you're absolutely correct. Or if you're British. Same thing. And the unit for time? This is a toughie. Careful. Yeah, seconds. We abbreviate that with an S. Unit for temperature. Well, we're going to use degrees Celsius and Kelvin. And yes, you do need to know the conversion between those two. Okay, so because the class is being taught in America, we also have to know this silly one, Fahrenheit. But mostly to be able to convert it to this one, so we can convert it to this one or this one to this one. So what do we use to measure the amount of a substance in chemistry? Ooh, this one should make you pause. How about a mole, aka a mole? So if we have 1 mole on this side of the scale, see, it's 1 mole. How many are over here? That's right, 6.022 times 10 to the 23rd. Don't forget to celebrate National Mole Day on October 23rd. Uncertainty and measurement, well, this is kind of where we start our introduction to the conversation of sig figs and why they're important. Well, they're important because they communicate to the reader some degree of uncertainty in your measurements. For example, take a look at this liquid in the graduated cylinder. What is the scale? That's the first thing you want to ask yourself. When trying to measure something, what is your scale here? Each line, each distance is what I mean by the scale. And in this case, our scale is 0.1 milliliters. So of what digits would you absolutely be certain? The ones place, the tenths place, the hundredths place? Well, we're absolutely certain of the first 2 digits. We're absolutely certain of this ones place. We know the liquid is in the 1. That's easy enough. See, we agree all the way across the board. And we're absolutely certain that this liquid is between the 0.1 and the 0.2. So these become our certain digits. Now the next one is, well, which one is our uncertain digits? All measurements have an uncertain or a guessed number. You guesstimate that last digit. I would take any one of those as a reasonable answer. The correct way to write it is you pick one of those. I'm going to go with the 1.15 because that's in the middle. And then I say it's plus or minus. Plus or minus, which means give or take my uncertain amount. Oh my gosh, something brand new. I really didn't discuss this in Gen Chem, so you're going to have to deal with this one. Accuracy versus precision. Wonder what the difference is. Well, all right, I'll tell you. Accuracy means it agrees with the true value. So if you look at this graph, everything along the X line is considered to be the true value. And each one of these blue dots represents your lab work. Well, in this case, I would say your lab work is pretty accurate. But is your lab work precise? We define precision as how well your measurements agree. So, if that line represents the true value, you are accurate. I would say you're fairly accurate, but are you precise? Yes, because there's not a lot of variation in your dots, you're also precise. So in this case, if this was your lab data, I would say you're both accurate and precise. What about this one? Is it accurate? No, it's not accurate. Look at how far it is from the true value. But are you precise? Yes, you are precise because the data set is pretty nicely clustered together. So yeah, you are precise. Not very accurate. Oh, I answered those. Ha, that's funny. Okay, if you're twisted. Take a look at this graph. Is the data accurate? Well, a couple of them are, but overall, no. Let's see, this one's pretty good, and this one, and this one, and the rest of it, not so much. Sort of. Less than 50%, so nah, not really. Are you precise? No, you're all over the place. So, no, this data is neither accurate or precise. Take a look at this one. Are you accurate? Yeah, two of the dots are. So, no. Are you precise? No. Again, your data points are all over the place. So no, you're not precise. All right. This is another way to describe precision and accuracy. So, take a look at this. We've all played darts? Yes? No? This is actually one sport I'm pretty good at, in case you wanted to know. Anyway, look at the dartboard. If your goal was to hit the bullseye, are you accurate? Yes. Are you precise? Yes. What about this one? If the goal is to hit the bullseye, are you accurate? That sounded funny. Are you accurate? Not at all. You're off my team. Are you precise? No, not that either. Now take a look at this one. Are you accurate? No. You're still not on my team. Are you precise? Yes, because all of your data points are clustered in the same place. So, you might have hopes on my team. I just got to get you to move those darts down a little. Here we go with the fun stuff. Sig figs. So, all non-zero digits are significant. So this one has how many sig figs? 4. This one has how many sig figs? Maybe I can hit it. Maybe not. There we go. How many sig figs there? 5. Captive zeros are always significant. Another word for this is sandwiched zeros. So in this one we have 3 sig figs. In this one we have, let's see, I'll write that, 3 sig figs. 1, 2, 3, 4, 5 sig figs. So zeros at the end of a number are significant if and only if there is a decimal point somewhere. For example, here's a decimal point and the zero's at the end. So this zero is considered significant and we have 4 sig figs there. There's a decimal point. This is at the end. So this zero is significant. This one is simply a placeholder, which I would like to see zeros before the decimal points, please. Anyway, 3 sig figs there. This zero is at the end of the number. There is a decimal point. Therefore, the zero is significant. So we have 4 sig figs. Last but not least, zeros at the end are significant if there's a decimal point somewhere. These 3 don't count for significance. They're not at the end. So this one has 2 sig figs. All other zeros are placeholders. They don't count. How many sig figs here? 1. How many here? 3. Here? 2. Let's take a look at all these numbers and zeros. So, does this very first zero, well, let me find that one. Okay, this one. Does that one count as significant? No. It's simply a placeholder, also called cosmetic purpose. Take a look at these 2. Where'd you go? Oh, pen. There we go. This one and this one. Are they significant? No. They just are placeholders. Let's take a look at the next 2 zeros. These are significant because they're captive or sandwiched. Those are significant because they're integers. They're non-zero numbers. They always count. And the last 2 zeros? Well, they're at the end with a decimal point somewhere. So it counts. So this number has a total of 1, 2, 3, 4, 5, 6, 7 sig figs. Now, counting sig figs. Exact numbers, well, you know what? We don't care, basically, is what all that means. These are exact numbers. 1 inch equals 2.54 centimeters. We don't use this. It's like a definition, and it doesn't go. The only thing that we use for sig figs is numbers we would have gathered by measurement. A number you look up is not going to be counted for sig figs. A number you count, well, 9 pencils, there's no ambiguity there. You can count, hopefully, the correct number of pencils. Also, the other one that I should mention right here, if you get a conversion off the periodic table, for instance, 22.99 grams of sodium equals 1 mole of sodium. That is also considered to be an exact number. A conversion does not count for sig figs. Multiplying and dividing, you're going to go by the number that has the least number of sig figs. I'll write that down for you. I'll even change my pen color just for you. Okay, so you're going to go with the number with the least amount of sig figs. So in this first term, we have 3 sig figs, and in the second term, we have 5 sig figs. Now, if I take those two numbers, punch them into the handy-dandy calculator, I get that. Does that have the correct number of sig figs? No. We need to round it to 3 sig figs. And I know for some reason a lot of kids struggle with this whole rounding to the correct number of sig figs. So we're going to try to fix it here. So we got 1, 2, 3. I only care about these first 3 digits. That's all I care about. However, this 8 says take the 0 and change it to a 1. Yeah, you got to round appropriately. There we have a final result with 3 sig figs. Now, to add and subtract, what we're looking for here is the answer with the least number of decimal places. You can only be as accurate as your crappiest measurement. So in this very first term, we have 3 decimal places. In this term, second term, we have 2 decimal places. So how many should be in our answer? Well, if I take my handy-dandy calculator, or actually just use math, it's not that tough really, and add it up, I get that. Is that enough decimal places? Or too many? Yeah, it's got too many. We can only be as good as the 2 decimal place term. So our answer should have 2. So your final answer should be, give it a try. What is it? What is it? There you go. Final answer.